Hello there, and welcome to Science for Sleep. I'm really glad you're here. Maybe it's late where you are. Maybe you've already brushed your teeth, dimmed the lights, settled into bed with your phone or tablet nearby. Maybe you're on the couch, still dressed from the day, just looking for something that doesn't rush, something quiet that lets your thoughts drift without pushing. Wherever you are, this is a space for that. A space for soft curiosity and slow science. If you're new here, this isn't a place for fast answers or flashy effects. There's no test at the end, and you don't need to know anything going in. These videos are meant for rest, for reflection, or just for the background of a quiet moment. The topics are big, but we don't tackle them. We wander through them, sometimes with answers, sometimes with questions, always slowly. Tonight we're asking something a little strange, something simple on the surface but more complicated the longer you think about it. Do black holes have a limit? Or can they just keep going forever, swallowing everything they touch, growing and growing without end? It's a question that doesn't need an immediate answer. It's something you can just carry for a while. Let it unfold slowly, like the night outside your window. Maybe you've thought about black holes before, maybe just in passing. Maybe you've seen an article, a simulation, a headline. They're easy to imagine as monsters. Huge, powerful, dark things that pull everything in and let nothing out. That idea is dramatic and a little frightening. But that's not really what they are. Not exactly. They're stranger than that and quieter. What time is it where you are? Midnight? Early morning? Maybe not even dark yet. Some people listen to these while winding down from work, others while they fall asleep, and a few just like a calm voice to fill the quiet. However you found this, and whenever, I'm glad you're here. I made this for you. If you find this gentle or useful or calming, feel free to give it a like or subscribe, but there's no pressure. The goal isn't to chase numbers or clicks. The goal is just to make something slow enough to feel real. So now we begin. Black holes. They're not holes, really. They're not objects either, in the usual sense. They're regions. Places where the pull of gravity becomes so intense that nothing, not even light, can escape. The term black hole is catchy, but it's misleading. They don't suck things in like vacuums. They don't move through space hunting for matter. They just sit waiting, silent, predictable, in a way. But still misunderstood. We know they exist. We've seen their effects. We've watched stars orbit invisible points. We've detected gravitational waves, faint ripples in space, caused by black holes merging. We've even taken a picture of a black hole's shadow, using a network of telescopes the size of the Earth. And every time we find a bigger one, a heavier one, the question gets louder. Can this keep going? Do black holes have an upper limit? Or could they eventually grow so large they swallow galaxies, maybe even the universe? There are lots of ideas, some scientific, some speculative. But like most big questions, it helps to start at the beginning. Not with what we don't know, but with what we do. We know black holes grow. That part is simple. They gain mass by pulling in matter, gas, dust, stars, even other black holes. When something crosses the event horizon, it doesn't bounce back. It adds to the total, a kind of one-way trip where everything falls in and nothing gets out. And because mass is tied to gravity, the more a black hole has, the stronger it gets. So then the next question is what stops it? Is there a physical limit, a natural balance? Or is there nothing to hold it back? To answer that, we'll have to look at how black holes form, what feeding actually looks like, and whether there's anything in the universe that pushes back when they start to grow too large. That's where we're headed. But we'll take it one quiet step at a time. When you first hear about black holes, it's easy to imagine them as hungry, as if they were alive in some way, waiting to consume whatever comes near. But hunger is a word we use for living things, for animals, people, creatures that need to eat to survive. Black holes don't need anything. They don't grow because they're trying to. They don't consume matter to stay alive. They simply respond to what's around them. If something falls in, they grow. If nothing does, they wait. Still, it's tempting to describe them with words like appetite or feeding. Because from our point of view, that's what it looks like. A black hole surrounded by swirling gas. Matter pulled inward, faster and faster, heating up before it disappears. Some of that matter never makes it inside. It orbits for a while, spirals closer, then gets caught in the pull. The gravity near a black hole is so intense that even atoms falling in generate energy. Heat, light, radiation is one of the brightest processes in the universe, even though the black hole itself remains completely dark. If that seems contradictory, something that bright orbiting something that dark, it is. But it's also real. The brightest objects in the known universe are called quasars, and at the centre of everyone is a black hole. A massive one. Not the kind born from a single star. The kind found at the centre of galaxies. The kind that weighs millions or even billions of times as much as our sun. These black holes are surrounded by matter moving at enormous speeds, releasing energy as it falls inward. That energy forms jets, sometimes shooting out in opposite directions for thousands of light years. The jets aren't coming from the black hole itself. They're coming from the area around it, from the chaos right before the quiet. When we see that kind of activity, it's easy to imagine a black hole as a predator, but it's more accurate to think of it as a drain. Not a suction or a mouth, just a point of no return. The shape of space around it changes so dramatically that once something crosses a certain boundary, there's no path back out. Not even for light. That boundary is called the event horizon. There's no wall or surface, you wouldn't notice crossing it. But once you do, there's no escaping. Everything past that point adds to the black hole's mass. It doesn't matter what goes in. Gas, dust, a star, another black hole. A black hole doesn't keep track. It doesn't have memory. Everything becomes part of the same mass, the same gravity, the same curve in space. But even though black holes don't choose what to absorb, they're shaped by what's available. If there's nothing nearby, they stay the same. Quiet. Hidden. If a cloud of gas passes too close, or a star drifts inward, they gain mass. It's not desire. It's not hunger. It's just the path of least resistance. Some black holes grow slowly. Little gas here, a little dust there. A gradual process that takes millions of years. Others grow in dramatic events, collisions, mergers. Entire stars pulled apart and fed into the black hole in just a few minutes. These events are rare, but when they happen, they release enormous amounts of energy. Telescopes can see them from billions of light years away. A brief flare, then silence again. The process of matter falling into a black hole is called accretion. It's not smooth, it's chaotic, turbulent. Particles crashing into each other, releasing heat as they spiral inward. That heat builds up and radiates outward, sometimes pushing against the matter trying to fall in. This is where something interesting happens. A balance forms. If a black hole tries to absorb too much too quickly, the energy being released pushes back. That push doesn't stop accretion, but it can slow it down. It limits how fast a black hole can grow. There's even a name for this balance. It's called the Eddington limit. It describes the point where the outward pressure of radiation equals the inward pull of gravity. If the black hole tries to grow faster than that limit, the pressure pushes matter away. Not permanently, just enough to slow things down. It's not a hard boundary. It doesn't cap the size of a black hole. But it does put a kind of governor on growth. A natural speed limit, not based on rules, but on cause and effect. So even though black holes have no mouths, no minds, no desire, they still follow patterns. They grow when something gets close. They grow faster when there's more to take in. But they never consume beyond what the surrounding space allows. That's why most black holes aren't constantly growing. They might go millions of years without gaining significant mass. If nothing falls in, they don't change. They don't reach out. They don't pull matter from far away. Gravity weakens with distance, and unless something gets close enough, the black hole is invisible, quiet, not pulling, just existing. And still, when we do find large black holes, we know they must have had long, complicated histories. To grow from the size of a star to something that outweighs billions of stars, there has to be a path. A slow collection of matter over time, a series of mergers, a lucky position in a dense part of a galaxy. Or maybe a period early in the universe when conditions were different, when gas was more abundant and everything was packed closer together. Some scientists think black holes may have formed directly from dense gas in the early universe, skipping the usual process of star death. If that's true, some black holes could have started large. Others may have had a head start by sitting at the centres of young galaxies, pulling in material while the structure around them was still forming. We're still piecing that part together. The early universe is hard to observe directly, but we know that black holes can grow fast under the right conditions. And if those conditions existed more commonly in the past, it could explain the giants we see today. But even giants don't grow forever. They can reach sizes that seem incredible to us, tens of billions of times the mass of the Sun. But even that has limits. Not because the black hole refuses more mass, but because there just isn't enough material nearby. Galaxies empty out. Gas clouds drift too far. Stars keep their distance. Feeding slows, and the black hole settles. Sometimes the surrounding galaxy runs out of matter to give. The black hole becomes dormant, not dead, just quiet. It still bends space, it still affects time, but it stops growing, at least for now. And unless something changes, a collision, a drift of gas, a wandering star, it stays that way, heavy, invisible, waiting. The idea of a black hole swallowing everything sounds dramatic, but that's not what happens. Most of the matter in a galaxy never comes close enough to fall in. Stars orbit at safe distances. Gas clouds spread out. Planets and solar systems live their whole lives without getting anywhere near the event horizon. The universe is big, and space is mostly empty. Black holes aren't sweeping through space collecting matter as they go. They're shaped by what comes near, nothing more. Still, we've seen what happens when matter gets too close. The signs are clear. Bright flares, jets of radiation, ripples in the structure of galaxies, and sometimes gravitational waves, visible tremors in space, created when two black holes merge. Those waves are faint, but we can detect them. We've been doing it for almost a decade now. Each one tells a story. Two black holes spiralling inward, colliding, and becoming one. When that happens, a portion of their mass is released as pure energy, not in light, not in heat, but in gravity. And then the new black hole is born, heavier, quieter. This is how growth works in space. Not with consumption, but with accumulation. Not through hunger, but through time. Black holes grow not because they want to, but because matter keeps falling in. And the question that follows is simple. What happens to all of that matter? Where does it go? Does it just vanish? To answer that, we have to look closer, not at the event horizon, but just beyond it, at the space where things fall in and the shape of space begins to bend. That's where growth becomes something more than just weight. That's where space itself starts to stretch. Size in space is rarely simple. There's distance, which stretches longer than anything we experience here on Earth. There's volume, which feels almost meaningless without comparison. And then there's mass, how much something truly weighs, not in pounds or kilograms, but in how it bends space, how it shapes gravity, how it affects everything near it. When we talk about black holes, size is measured in mass, not in width, not in depth, not in how tall it would be if you stood beside it. It's about how much material has been compacted into a region of space so dense, so tightly curved, that not even light can escape. The smallest black holes we know of are about the size of a city, maybe 20 kilometers across, but their mass is 2 or 3 times greater than our Sun. Not the surface of the Sun, not the light, the full weight of it, pulled down and packed tightly into a point. And that's just the beginning. A black hole that's 10 times the mass of the Sun isn't 10 times wider. It's still compact, still invisible. Its event horizon is only a few dozen kilometres across. You could drive around it in an hour, if there were roads, and if driving near a black hole were a good idea. But what matters isn't the width, it's the gravity, the pull, the way space stretches near it. Now scale that up. There are black holes out there, confirmed ones, that are millions of times more massive than the Sun. We call these supermassive black holes. They sit at the centres of galaxies, including our own. In the middle of the Milky Way, 26,000 light-years from Earth, there's a black hole about 4 million times the mass of the Sun. We've never seen it directly, but we've seen stars orbit around it. Not randomly, not chaotically, but in perfect paths, moving at impossible speeds, bent by a gravity strong enough to hold them in tight curves for decades at a time. 4 million suns, all packed into a region smaller than our solar system. And that's not even close to the biggest. In other galaxies, far larger, far older, we've measured black holes with masses in the billions. One of the largest we've found so far is Photon 618. It sits more than 10 billion light-years away, meaning we're seeing it as it was 10 billion years ago. Even back then, it had already grown massive. Estimates put its mass around 66 billion times that of our Sun. That number doesn't feel real, but it's what the data shows. If you try to compare it to everyday objects, it falls apart quickly. Even if you imagined our entire solar system, planets, moons, asteroids, all of it, Photon 618 could swallow it with room to spare. If you placed it where the Sun is now, its event horizon would stretch past the orbit of Neptune. Not in theory, in actual size. But again, that's not the most important part. What matters is what it does to space, what it does to time. That much mass in one place bends everything around it. It slows the clocks. It changes the paths of light. It carves a deep well in the structure of the universe, and everything nearby moves in response. The question then becomes, is there a ceiling? Can a black hole keep growing beyond that? Could it be 100 billion times the mass of the Sun? 1 trillion? What stops it? Technically, nothing about the black hole itself sets a maximum. It doesn't reach a point where it refuses more mass. If something crosses the event horizon, it adds to the total. The limits, if they exist, come from the environment. A black hole can only grow if there's material around to feed it. Gas, stars, dust, or another black hole. And even then, it takes time. The larger it gets, the slower the growth becomes, especially when the nearby material thins out. That's why most of the black holes we observe are in a kind of balance. They're large, but not absurdly so. They grow during periods of activity, galactic collisions, dense gas flows, then settle down, not dead, just waiting. And sometimes we catch them during those quiet phases. No bright accretion disks, no jets, just a heavy centre, keeping stars in orbit by gravity alone. Still, even with those limits, we continue to find black holes that challenge expectations, ones that are heavier than any star could have produced on its own. That's when we begin to look at their histories, mergers, ancient feeding frenzies, early universe conditions that may have allowed rapid growth. The story of a black hole's size is a story of everything it's ever touched, every piece of matter it's absorbed, every other black hole it's merged with, every nearby gas cloud it's drawn in. And that brings us to something important. A black hole's mass isn't always a record of its appetite. It's a record of its opportunities. You can place a black hole in a quiet part of space, and it will barely grow at all. Put the same black hole in the centre of a young crowded galaxy, and it will gain mass quickly. The difference isn't in the black hole, it's in what surrounds it. This is one of the reasons we believe there are different types of black holes, not just by size, but by origin. Stellar mass black holes form when massive stars collapse. They're small by cosmic standards, but still powerful. Intermediate mass black holes are harder to find, but they seem to bridge the gap, perhaps formed by clusters of stars collapsing together or small mergers over time. And then there are the supermassive ones, formed early, grown steadily, anchoring entire galaxies. The difference between a black hole with 10 solar masses and one with 10 billion isn't just size, it's context, time, location, and in a way, chance. Some researchers have even proposed the existence of ultramassive black holes, objects even larger than Ton 618. If they exist, they would be hiding at the centres of the largest galaxies, maybe in regions of space we haven't studied closely enough. Their event horizons would be enormous, but their effects from a distance would still follow the same rules. Gravity, curved space, slowed time. The details change, but the shape of the influence remains, and that's one of the strangest parts about black holes. No matter how big they get, they're simple in structure. We can describe them using just a few numbers: mass, spin, electric charge. That's it. Not what they're made of, not what they've consumed, just the measurable traits that affect how they interact with the rest of the universe. So when we ask how big is big, the answer isn't a number. It's a reminder that size doesn't come from ambition. It comes from history, from time, from the environment that allowed something quiet to become something vast. And still, no matter how large a black hole becomes, there's always the question of what's next. Does it stay the same forever? Can it keep growing? Is there something, somewhere, that pushes back hard enough to stop it completely? To find that answer, we need to look at the space around a black hole, at the material just outside the event horizon, at what feeding actually looks like, and how space itself reacts when a black hole gains mass. Because that's where things start to shift, not just in numbers, but in the very structure of the universe nearby. The largest black holes we've found didn't show themselves all at once. They weren't sitting in plain view. They were inferred, measured, confirmed step by step. Some of them were suspected for years before being fully accepted, and even now when we say we've found the biggest ones, we're probably only seeing a fraction of what's out there. Our instruments are good, but they're limited by distance, by light, by interference from dust and gas. So it's likely there are heavier black holes, quieter ones, waiting in parts of the sky we haven't resolved yet. But based on what we can observe, a few stand out. The black hole at the centre of the galaxy M87 is one of the most well known. Not because it's the biggest, but because in 2019 we captured the first image of its shadow. Not the black hole itself, but the region where light bends and wraps around it. That black hole weighs around 6.5 billion times the mass of our Sun. Its presence was suspected for decades. The galaxy it anchors has a bright jet of material extending from its centre, a jet powered by matter falling into the black hole and being redirected at nearly the speed of light. That kind of structure doesn't appear on its own. It's shaped by something massive, something rotating, something invisible. When the Event Horizon Telescope collaboration released that image, it wasn't sharp in the way space photos usually are. It looked like a blurry ring, a soft edge around a dark core, but it was the first visual confirmation of something we had only theorized. It matched the predictions of general relativity exactly. The shape, the size, the light distortion, all of it confirmed that the structure in the middle of M87 wasn't just heavy. It was a black hole, and a large one. Still, as massive as M87's black hole is, it's not the largest we've found. That distinction currently belongs to a handful of extreme candidates. One of them is Ton 618, a quasar located in the distant universe. The numbers attached to it are difficult to process. The black hole at its centre is estimated to weigh around 66 billion solar masses. It's so far away that the light we see from it began its journey over 10 billion years ago. That means it reached this size very early in cosmic history, possibly within the first few billion years after the Big Bang. We don't know exactly how it got so big, so fast. It's part of a larger puzzle in astrophysics, trying to understand how supermassive black holes formed so early in the universe. The process of growth through steady accretion is too slow to explain these objects on its own. There are hypotheses. Some suggest they formed from the collapse of massive clouds of gas instead of stars. Others think they grew through early, frequent mergers in a more compact universe. But there's no clear answer yet. What we do know is that black holes like TON 618 are rare. Quasars are the active centres of galaxies with high energy emissions, are more common in the early universe than they are now. That suggests black holes did most of their growing early, during a time when gas was more available and galaxies were more chaotic. In today's universe, most of the giant black holes are relatively quiet. Not inactive, but no longer in the kind of feeding frenzies that built them up in the first place. There's another candidate even larger, though not yet as well confirmed. Some measurements suggest that the central black hole in the galaxy, Holm 15A, may be close to 40 billion solar masses. Unlike quasars, Holm 15A is more local, located about 700 million light-years away. It doesn't shine with high-energy jets or blinding radiation. It's not active in the way early universe quasars are, but its core is diffuse, and the motion of stars around it suggests a central object too massive to be anything else. When astronomers measure these black holes, they look at the speeds and paths of stars near the centre. The faster the stars move, the more mass must be present to hold them in orbit. And when the speeds reach a certain point and no visible matter can explain the motion, the conclusion becomes clear. A black hole is there. Massive. Invisible. Shaping everything around it. Some galaxies might host even larger ones. Especially giant elliptical galaxies at the centres of clusters, where material has been pulled inward for billions of years. But the farther away they are, the harder they are to measure. The light is faint and the details are small. Our instruments are improving though. New telescopes, both on the ground and in orbit, are being designed with this kind of detection in mind. As they come online, we'll almost certainly find heavier black holes. Whether they're 10 billion or 100 billion solar masses, they'll stretch our understanding of how gravity can shape matter on the larger scales. But size in these cases is only one part of the story. What's just as interesting is how these giants affect their surroundings. A black hole at the centre of a galaxy isn't just a passenger, it shapes the entire structure. It influences star formation, gas movement, even the shape of the galaxy itself. When active, these black holes release enormous amounts of energy, often through jets that travel thousands of light-years and heat up the surrounding gas. That heat can prevent new stars from forming. It can regulate the growth of the galaxy. It's not just that the galaxy feeds the black hole in turn controls parts of the galaxy. This feedback loop is still being studied, but the pattern is clear. The largest galaxies tend to have the largest black holes, and those black holes, when active, slow down the formation of new stars. In a way, the black hole sets a limit, not by devouring everything, but by changing the conditions around it. That's part of why the biggest black holes don't grow forever. Eventually they run out of easy material to absorb. The gas becomes too hot or too sparse. Stars keep their distance. The environment stabilizes. Growth slows. 1 billion years ago, the same black hole may have been glowing brightly, surrounded by swirling matter releasing powerful radiation. But today it may be nearly silent. Still there. Still massive. But no longer growing at the same rate. And yet it's never completely still. If another black hole drifts close, maybe after a galactic merger, the two may begin to spiral together. The process takes millions of years, but the end result is another increase in mass. The biggest black holes are built from many moments like that. Slow, invisible gatherings of weight over cosmic time. Even now, some of these giants may be growing. Quietly, subtly, hidden behind clouds of dust or far beyond the reach of our instruments. Others may already have reached their peak, settled into the centre of their galaxies, affecting everything nearby, but no longer changing much themselves. We tend to imagine the biggest things as being the most dangerous, but black holes, even the largest ones, aren't threats to the universe. They're part of its structure. They don't swallow everything. They take in what comes close and ignore what stays far. The vast majority of stars in any galaxy orbit well outside the reach of the central black hole. They feel its presence, but they're not in danger. They move through space as they always have, guided more by the overall gravity of the galaxy than by the single point at the centre. The scale of these objects is hard to hold in your mind. A black hole with billions of solar masses doesn't just bend space. It stretches time, distorts light, and influences the flow of matter for thousands of light years. And yet, from a distance, it reveals almost nothing. No light, no surface, just a shadow or a wobble, or a bright disk of gas that hasn't fallen in yet. These are the biggest we've seen, the quiet giants, the deep wells at the centres of galaxies, and each one tells us something about how matter moves through space, how gravity shapes the universe, and how even the darkest places can teach us something about light. But knowing how big a black hole can get leads to another question. What happens when it takes in something large, something like a star or a planet or an entire cloud of gas? What does that moment look like, and how does it change the black hole? When a black hole takes in new material, it doesn't swallow it like a mouth. There's no bite, no gulp, no visible moment when the matter disappears. From the outside, the process is more gradual, more structured, more complicated, but also more revealing. The first thing to understand is that nothing falls directly in. Not from a distance, not in a straight line. Matter that ends up inside a black hole almost always starts by orbiting it. Gas, dust, fragments of stars, whatever the material is, it starts to move in long spirals, like water circling a drain. These spirals form what we call an accretion disk. An accretion disk isn't a solid thing. It's made of matter stretched thin, rotating at incredible speeds, compressing and colliding as it closes in. The closer the material gets to the black hole, the faster it spins. Friction builds. The collisions generate heat. A lot of it. Temperatures rise to millions of degrees. The matter glows, not just in visible light, but in X-rays and gamma rays. These emissions are what we actually detect when we observe feeding black holes. Not the black hole itself, but the chaos just outside it. The disk is hot, but it's also relatively flat. It thins out as it extends from the event horizon, sometimes for thousands of kilometres, depending on the black hole's mass and the amount of matter available. As material spirals inward, it loses angular momentum. That's what allows it to move closer. Bit by bit, it gives up energy, falls lower in the well of gravity, and eventually crosses the event horizon. From that point on, the material is gone. Not destroyed, not vaporized, just no longer visible, no longer reachable. It becomes part of the black hole's mass. The horizon grows, gravity deepens. The black hole is now heavier than it was before. But to an outside observer, the moment of falling in looks different. Time near the event horizon slows down, not metaphorically, but physically. From a distance, you'd see the infalling matter stretch and dim. The light it gives off would shift toward the red end of the spectrum. It would appear to slow down, fade, and never quite cross the horizon. This isn't an illusion. It's a real effect of gravity on time and light. In practice, the material does fall in, but from the outside, it's as if it gets frozen at the edge. The energy released before the material disappears is often more dramatic than the fall itself. When gas compresses and heats up, it can emit intense radiation. Some of it escapes. Some of it is redirected. In highly active systems, the magnetic fields near the accretion disk twist and channel material outward in narrow beams. These beams become jets, long, thin streams of particles moving at nearly the speed of light, shooting away from the black hole's poles. Jets are among the most powerful phenomena in the universe. They don't come from inside the black hole. They come from the region just outside, where magnetic fields are strongest and energy is being released in enormous amounts. We've observed these jets extending for thousands of light years, well beyond the host galaxy. They carry energy, matter and momentum outward into intergalactic space. Not every feeding event produces a jet. The conditions have to be right. Enough material, the right spin, a strong magnetic field. But when it happens, it's hard to miss. Even if the black hole itself is invisible, the effects of feeding can light up the sky. Sometimes the matter falling in isn't gas, it's a star. When a star passes too close to a black hole, tidal forces begin to stretch it. The gravity on the side of the star closer to the black hole is stronger than on the far side. That difference starts to pull the star apart. If the encounter is close enough, the star is torn into long streams of gas. Part of the material is flung away, part of it falls inward. These events are called tidal disruption events, and they're rare, but we've seen them. The light curve changes, the spectrum shifts. A flash appears in a region of the sky that was quiet just days earlier. These flares don't last long, a few weeks, maybe a few months, but they reveal what black holes are doing when something large crosses too close. The feeding is fast, the accretion is chaotic, and then the system returns to silence. Even larger feeding events can happen when galaxies collide. In those cases, the central black holes may eventually merge, but before they do, there's usually an increase in available material. Gas from one galaxy flows toward the center of the other. Accretion ramps up. The black hole enters a period of intense growth. It absorbs mass, releases radiation, and potentially creates new jets. These phases can last millions of years. Over time, the available matter runs out. The gas disperses, the feeding slows, the black hole stabilizes at a new, larger mass, and once again it becomes quiet. So what really happens when a black hole eats? Matter spirals inward. It heats up. It glows. It moves faster and faster until it crosses the point of no return. The black hole's mass increases. Its event horizon grows. Its gravity becomes slightly stronger. The changes are invisible from the outside, except for the effects on surrounding space. If the feeding was sudden, there may be radiation, a flare, a jet, a burst of energy that tells us something just changed. But from a distance, the black hole doesn't move. It doesn't flicker. It doesn't expand like a balloon. It simply grows deeper, heavier, quieter than before. All of this leads to a quiet understanding. Black holes don't eat in the way we eat. They don't consume because they need to. They grow because matter gets close. And as long as there's something to fall in, they'll keep growing. There's no point where they get full, no moment where they stop accepting mass. The only thing that limits a black hole's growth is what's available nearby and how fast it can fall in. Still, when we think of eating, we also think of waste, of what's left behind. But black holes don't leave anything. Nothing escapes, except maybe, possibly, over very long time scales, through processes we barely understand. That's where the next question appears. What happens to the star, or the gas, or the light after it falls in? Is it gone completely, or is it stored somehow? Changed? Is there still something left behind, even if we can't see it? That's the puzzle physicists are still trying to solve. And to get closer, we need to understand more than just what black holes take in. We need to ask whether anything anywhere ever comes back out. We know that black holes can pull in gas and dust. We've seen it. The process is messy but measurable. But what about larger things? Can a black hole swallow a star, an entire fusion-powered ball of plasma, millions of kilometers wide, burning at its core, radiating heat and light? The answer is yes. And it happens more often than you might expect. Stars wander. Even in galaxies with billions of them, they move in orbits shaped by gravity and time. Most of those paths are stable. They pass through the galaxy, around the centre, never getting close enough to encounter real danger. But galaxies are old, and stars don't move alone. They can be nudged by gravity. They can pass too near to other stars or large clouds of gas. And when that happens, their orbits shift slightly. If one of those shifts sends a star too close to the centre of a galaxy, and if a black hole is waiting there, then a different kind of interaction begins. The closer the star gets, the more gravity starts to affect it, not just by pulling, but by stretching. That effect has a name: tidal forces. The side of the star facing the black hole feels a stronger pull than the far side. That difference can become extreme. If the black hole is small, the star might actually cross the event horizon before being completely pulled apart. But if the black hole is large, the tidal forces start to tear the star apart before it gets anywhere near the centre. This kind of event is called a tidal disruption, and while it's rare on a human timescale, we've detected several over the last few decades. From Earth, we see it as a sudden burst of light in a place that was previously dark, a flash, a flare, a change in spectrum. These signs tell us that something large, likely a star, just got too close to a black hole. The process unfolds over days or weeks. The star is stretched into a long stream of gas. That gas wraps around the black hole, some of it escaping back into space, the rest falling inward. As the gas spirals in, it heats up. The glow increases, peaks and fades. The whole event might last a few months from beginning to end. Afterward, the black hole is slightly more massive. The star is gone. There's no explosion, no visible trace left behind, just a shift in mass, a small change in the surrounding gravity. From the outside, it's easy to miss, but telescopes built to detect transient light sources can pick up these changes. They've become some of the most reliable ways to observe black holes indirectly. Because when a black hole swallows a star, it leaves behind a fingerprint, not of the star itself, but of the process. Not all stars that pass close to black holes are torn apart. If a star's path is wide enough, or if it passes by quickly, it might escape. It could be flung outward on a new trajectory, moving faster than before. Sometimes stars are stretched but survive. Other times they're captured into an orbit, circling the black hole at a safe distance, repeating the near-miss every few decades. These interactions tell us more about the gravity near black holes than the black holes themselves. But when a star does get pulled in, the effect is final. The core breaks apart, the light fades, and the star is never seen again. In smaller black holes, the process is more direct. A star that gets too close may simply fall past the event horizon in one piece, without time to be stretched or shredded. The result is the same, a gain in mass, and no way to retrieve what's been lost. But for larger black holes, especially supermassive ones, the range of tidal forces is wide. There's more room for dramatic disruption, for visible effects, for extended flares that we can detect from halfway across the universe. Each time we observe one, we learn something about how stars behave near extreme gravity, about how black holes grow, and about what happens in the space just outside the point of no return. These events are powerful, but they don't change the shape of the galaxy. A single star being swallowed doesn't shift the orbit of its neighbours. It doesn't send out shockwaves. It doesn't destabilise the core. The galaxy continues as before, with one fewer star and a slightly heavier black hole, and yet over time these interactions add up. A black hole at the centre of a galaxy may absorb thousands, even millions of stars over billions of years. Not all at once, not quickly, but steadily, gradually, as gravity does its quiet work. Some galaxies have been observed with cores that are unusually empty, not in terms of gas, but in terms of stars. These cores may have been eroded by black hole activity, not through destruction, but through consumption. Stars falling inward, one by one, lost forever. But black holes don't go looking for stars. They don't pull them from far away. The stars have to get close, and in most galaxies, most of the time, that doesn't happen. The orbits are stable, the distances are large, the centre remains quiet. That's part of why Earth and our solar system is safe. We're nowhere near the black hole at the centre of the Milky Way. That black hole is real, about 4 million times the mass of the Sun, but it's also 26,000 light-years away. That distance is enough that its gravity doesn't affect us directly. The The sun's pull is much stronger here. The black hole is something we observe, not something we feel. The stars we can see moving around that central black hole, the ones we've tracked with precision over the years, are incredibly close to it by galactic standards. And even they don't fall in. They orbit, fast but stable, safe unless something changes. So while black holes can swallow stars, they don't do it constantly. They don't vacuum up everything in reach. They wait. And sometimes something comes close enough. These moments are rare, but they're reminders of how much energy exists in systems we usually think of as quiet. A single star, disrupted by a black hole, can release more energy in a few weeks than the sun will emit in its entire lifetime. Not because of destruction, but because of transformation. Gravitational energy turned into heat, motion, and light. But what about smaller things? If a black hole can absorb a star, can it also swallow something like a planet? Planets are small compared to stars. They don't produce their own light. They don't undergo fusion. But they're solid, often dense, and sometimes layered with complex structures, atmospheres, magnetic fields, even geological activity. They feel familiar because we live on one. So the idea of a planet falling into a black hole feels more personal somehow, less abstract, less distant. Yes, a black hole can swallow a planet. The process, in principle, is no different than with anything else. If an object crosses the event horizon, it becomes part of the black hole. The object's shape, composition, temperature, and surface features no longer matter. All that's left is its mass, and the effect that mass has on gravity. The black hole gains weight, and its event horizon expands slightly. But planets don't usually fall into black holes, not because black holes can't absorb them, but because the orbits of planets, especially the ones that form around stars far from galactic centres, are incredibly stable. Most black holes are either the remnants of stars or the central bodies in galaxies. The ones that could encounter planets typically aren't near them to begin with. And even if a black hole passes through a region with stars and planets, the likelihood of a direct interaction is low. Space is enormous. Distances between objects are measured in light years. The vast majority of planets will never come close to a black hole. Still, it's worth asking. What would happen if one did? If a planet were on a path that brought it close enough to a black hole, the first signs of change wouldn't be visible. They would be gravitational. The orbit would shift. The speed would increase. If the planet got too close, it might be torn apart by tidal forces. Just like stars, planets can be stretched. The gravity on one side becomes significantly stronger than the gravity on the other. That difference creates strain. If the black hole is large, the planet could be pulled apart before it even reaches the event horizon. The pieces would spiral inward, forming a brief, faint accretion disk. The debris would heat up slightly, depending on the speed and the material. Rocky fragments, metal cores, atmospheric gases, all of it would follow the same path. None of it would escape. The radiation given off in this process would be weaker than in a stellar disruption event, but still detectable with the right instruments. A small flash, a brief shift in background emissions. In practice, we haven't directly observed a planet falling into a black hole, but simulations show us what to expect. The energy release would be smaller than a star, but still measurable. It would depend on the size of the black hole and the speed of the encounter. If the black hole is very massive, the tidal forces might be less extreme. The planet could fall in more cleanly without being pulled apart first. It would simply cross the event horizon and disappear. From the outside, nothing would look different. No physical change in the black hole's appearance. No sound, no visible mark. Just a small addition of mass, and maybe a faint ripple of light or heat before the end. Theoretically, even Earth could be consumed by a black hole, if one were to pass close enough and align with our orbit. But this kind of event is so unlikely that it's not something astrophysicists consider a real threat. The nearest known black hole is thousands of light years away, and none are moving toward us. Even if one were passing through the galaxy, the chance of it coming close enough to affect Earth is extremely low. Less than low. Negligible. But hypothetically, if a black hole did approach our solar system, the gravitational changes would be felt before anything was seen. Orbits would shift. Planets might move out of alignment. Tidal stresses would begin long before the black hole itself became visible. And if Earth were on a path toward it, we wouldn't fall in suddenly. It would happen gradually. A slow spiral with accelerating changes to gravity, light, and time. And if we reached the event horizon, we wouldn't notice the moment it happened. The laws of physics near that boundary are precise but counterintuitive. Time slows, light stretches. The path inward becomes the only possible one. From the inside, everything continues normally until it doesn't. From the outside, it looks like time freezes at the edge. The planet in this scenario would be gone. No pieces, no remains, just a slightly more massive black hole. Larger planets, gas giants like Jupiter, might produce more observable effects. Their atmospheres could stretch into long glowing filaments. Friction might heat them enough to emit visible light. Telescopes could spot the flare. Spectral analysis might even identify elements in the planet's atmosphere as it falls apart. But even then, the moment of disappearance would still be quiet. Black holes don't chew or crush. They don't rip things apart on contact. They reshape the space around them, and when something enters that space, it follows the geometry. Downward, inward, irretrievably. In galactic centres, where stars and planets are more densely packed, it's possible that planets have been absorbed before. We just don't have the resolution or detection tools to see every event. Over billions of years, countless planets may have fallen into black holes, unnoticed except as minor changes in energy output or background noise. In some theories, black holes that consume matter retain a record of what fell in, not physically, but mathematically. This is the basis for ongoing debates about information loss and quantum theory. If a planet is swallowed, is the information about its state, its position, structure, velocity, gone forever? Or is it somehow encoded in the black hole's event horizon or radiation? That's not something we can answer fully yet. It's an open problem in physics, one that leads toward quantum gravity, string theory, and ideas still being tested. But it starts with the same basic fact. Yes, black holes can swallow planets, and yes, it changes them. Slightly, permanently. And what about us? It's a natural question. If a planet like Earth can fall in, and if nothing escapes, then what would happen to the people, the objects, the signals that were part of it? That's where things turn theoretical. Not just in terms of what we can see, but in terms of what we believe space and time can do. Time isn't fixed. It's not a constant background that ticks evenly everywhere. That's something we used to believe before Einstein, before the idea that space and time are part of the same thing, a flexible structure that bends when mass is present. In everyday life, we don't notice those bends. The Earth's gravity affects time slightly, but not enough to feel. Even between the surface of the Earth and a satellite orbiting above, the difference is only a few microseconds per day. But near a black hole, the effect is impossible to ignore. Time slows down in the presence of gravity. The stronger the gravitational field, the slower time moves relative to regions farther away. This isn't a theory in the abstract sense. It's been tested. We see it in GPS satellites, which need to adjust for time dilation caused by both speed and altitude. We've confirmed it in laboratory experiments using atomic clocks placed at different heights. Time, as far as we can measure it, runs faster the farther you are from a massive object. Black holes take that effect to the extreme. The closer you get to the event horizon, the slower time passes, not just for you, but in comparison to an outside observer. You wouldn't notice the change yourself. Your heartbeat would feel normal. A second would still feel like a second. But someone watching from a distance would see you slow down. Your motions, your signals, your presence, all stretched, delayed, faded. And as you approach the event horizon, the dilation becomes infinite. From far away it would appear that you never quite crossed the boundary. Your image would hover, red-shifted and dim, frozen in time just above the surface. In reality, you would fall in. But the outside world would never see that moment. Time, from your point of view, would continue. But from theirs, it would come to a stop. This is one of the strangest consequences of general relativity. That time is not a fixed experience. That depending on where you are and how fast you're moving, time itself stretches or compresses. In the case of a black hole, the warping is so severe that two observers can disagree completely about what's happening and still both be correct in their own frames of reference. If you hover just above the event horizon, assuming you could survive, which physics doesn't allow, you'd experience time moving normally. But if you looked out at the rest of the universe, everything would appear to speed up. Galaxies would rotate faster, stars would evolve in moments. Cosmic events that take millions of years could pass in what feels like seconds. From the outside, though, anyone watching you would see you freeze. Not all at once, but gradually. Your movement would slow, your light would redden, fade, and eventually you'd vanish from visibility. Not by disappearing, but by stretching so far in time that no new signal could reach the outside. This effect isn't just theoretical. It's part of how we detect black holes. The light emitted by matter near the event horizon gets redshifted, meaning its wavelength stretches. That redshift can be measured. It tells us how deep in the gravitational well the light came from, and when the shift becomes extreme, we know the source is close to a black hole. Time dilation near black holes is a reminder that our experience of time is limited by where we are. What feels normal to us is entirely dependent on our gravitational environment. We think of time as a shared experience, but the universe doesn't treat it that way. And it's not just time that changes. The same distortion affects space, energy, and motion. That's what creates the event horizon in the first place. Not a physical barrier, but a boundary beyond which the paths through space and time all lead inward. Once crossed, there's no trajectory that leads back out. Inside the event horizon, the curvature of space-time becomes so steep that all possible directions point toward the centre. That includes the direction we would normally think of as forward in time. In a way, falling into a black hole is like moving forward through time. Only the future leads inevitably to the singularity. But that raises deeper questions. If time is so distorted near a black hole, then what happens to the experience of someone who falls in? Do they reach the centre instantly? Do they have time to think, to observe, to feel? The answer depends on the size of the black hole. In small black holes, those formed by the collapse of massive stars, the tidal forces are so strong that you'd be stretched and compressed long before you reach the event horizon. The experience would be brief and violent, but in larger black holes, especially supermassive ones, the gradient in gravity is gentler. You could cross the event horizon without feeling anything at all. Time would seem normal from your point of view. You might even have minutes or hours of continued experience before reaching the singularity. No one knows for certain. It's beyond the point where we can measure or test. From the outside, no information about that journey can escape. Once you've passed the horizon, your signals can't reach anyone. Not because they're blocked, but because the structure of space-time itself prevents it. The light you emit can't climb back out. It curves inward, caught in the gravity well, just like you. This separation between what's experienced inside and what's observable outside is one of the reasons black holes are so mysterious. They are physical, predictable, and consistent with the laws of general relativity, and yet they create situations where information becomes inaccessible, where timelines diverge, and where cause and effect are hard to track from multiple perspectives. Time, near a black hole, becomes something else. It's not just slower, it's reshaped. The path you take through space and time is dictated by gravity, and in the most extreme cases, all roads lead inward. Not metaphorically, but literally. There's no direction that escapes. The geometry makes escape impossible, not by force, but by design. And while this distortion of time makes black holes fascinating to physicists, it also makes them difficult to study directly. We can only observe the edge, the region outside, the fading light of things that came close but didn't return. Everything else, the interior, the core, the singularity, is sealed off by the structure of time itself. But what about light? If time slows and curves near a black hole, what happens to light that passes nearby, or tries to escape from just outside the horizon? Light doesn't have mass, but it still follows the shape of gravity. That's one of the more surprising consequences of general relativity. In a Newtonian view, gravity only affects objects with mass. But in Einstein's model, gravity is the curvature of space-time itself, and light, even though massless, has no choice but to follow that curve. This is how we know black holes exist, even though we can't see them directly. Light that passes near a black hole bends, sometimes just a little, sometimes dramatically. If the light comes too close, it can enter orbit. If it gets closer still, it doesn't escape at all. There's a precise distance from the centre of a black hole, where light can, in theory, orbit it in a perfect circle. That distance is called the photon sphere. It's not a surface or a ring in the usual sense, just a zone where the gravitational pull is strong enough to keep light trapped in a closed loop. But the orbit isn't stable. A small disturbance and the light either escapes or falls in. Outside the photon sphere, light that travels past a black hole gets bent. The closer it passes, the sharper the curve. In some cases, the light from a background object, a star, a galaxy, gets bent so much that it wraps around the black hole and reaches us from the opposite direction. This effect is called gravitational lensing. Gravitational lensing doesn't just prove that black holes affect light, it also gives us a way to map the invisible. When we see a distorted image, a stretched or duplicated galaxy, we can trace the shape of the lens that caused it, and often the source of that lens is a black hole, or a dense cluster of matter we can't see directly. Light behaves predictably in curved space-time. If it travels through flat space, it moves in a straight line. If space is curved, the line curves with it. That's what makes black holes so striking. They're not just heavy. They bend the fabric of reality so tightly that light, which normally escapes everything, can be redirected, trapped, or absorbed. Just outside the event horizon, light begins to struggle. If it's emitted from matter falling in, from gas in the accretion disk, for example, the light that travels outward has to climb out of a deep gravity well, and in doing so, it loses energy. That energy loss doesn't mean the light stops, it just shifts. The wavelength stretches, the colour reddens. This shift is called gravitational redshift. It's similar in concept to the Doppler effect, but instead of motion, the shift comes from gravity. The stronger the gravity, the more energy the light loses as it escapes. In extreme cases, the light becomes so redshifted that it slips beyond the range of our instruments. We can't detect it anymore, even though it was emitted just outside the event horizon. That's why the edge of a black hole looks dark. Not because there's no light being produced, but because most of it never escapes. The light either falls back in or stretches so far that we can't see it. What we do see is the material just outside that edge. Hot gas, compressed and glowing, briefly visible before it disappears. When the Event Horizon Telescope captured the first image of a black hole's shadow, it was showing us exactly this. The area where light bends so sharply that almost none of it escapes. The ring around the shadow isn't the black hole itself. It's the light from matter orbiting nearby, curved into a bright ring by the black hole's gravity. The dark centre is where the light goes in and never comes back. From the outside, this creates a perfect silhouette, not because there's a surface, but because the structure of space prevents light from crossing back outward. The black hole doesn't block light, it traps it. But trapping isn't always complete. Some light, emitted from far away, can skim past the event horizon without being absorbed. If it arrives at just the right angle and speed, it can curve and continue outward. That's how we get images of material close to the black hole, but not inside it. That's how we see the jet, the disk, the distortion. Not from within, but from just outside the line where space curves too steeply. It's also why black holes don't appear black in the usual sense. In isolation, with no material falling in, a black hole wouldn't emit or reflect any light. It would be invisible. But when surrounded by matter, as most large black holes are, they become visible by proxy. We see the light from the things they haven't consumed yet. That light tells us a lot. Its spectrum reveals the elements present in the gas. Its polarization tells us about magnetic fields. Its shape tells us about rotation and spin. Every photon that escapes from the edge of a black hole carries a trace of what happened near it. But the ones that don't escape, the ones that fall in, are lost. Not in a poetic sense, but in a literal one. We can't see them. We can't follow them. They pass the horizon and cease to have any connection to the rest of the universe. Their energy, their direction, their history, all absorbed into the mass of the black hole. That's what makes the question of information so hard. If light carries information, and if light can fall into a black hole and disappear, then is that information destroyed? Or is it somehow preserved? Encoded in the black hole's properties? Released slowly through radiation? These are the questions that come next. Not just about light itself, but about what it represents. Because if nothing escapes a black hole, not even light, then how do we ever learn anything about what's inside? If a black hole pulls everything inward, with no way out, it's natural to wonder where all that inward motion leads. What happens once something crosses the event horizon? Where does it go? Is there a place, a bottom, where all of it collects? The simplest model says yes, but not in a way that's easy to imagine. According to classical general relativity, everything that falls into a black hole ends up at the centre, not scattered or floating or stored, not collected like objects in a container, but compressed, all of it, into a single point of infinite density and zero volume. That point is called a singularity. It isn't a structure. It's not a ball of matter packed tightly. It's a breakdown in the math. A place where the equations that describe gravity stop working. The density becomes infinite. The curvature of space-time becomes infinite. And time, as we understand it, reaches an endpoint. The singularity is not a bottom in the physical sense. It's a limit. A point where our current theories lose their ability to describe reality. In the Schwarzschild model, a non-rotating uncharged black hole, the singularity exists at a single point in space at the very centre. Everything that crosses the event horizon falls inward toward that point in a finite amount of time, at least from the point of view of the thing falling in. There's no way to stop, slow down or turn back. The geometry of space-time forces everything to move in one direction, toward the centre. But real black holes aren't simple. They spin. Many have charge. When those factors are added into the equations, the structure changes. Instead of a single point, the singularity may become a ring. In some solutions, that ring creates a theoretical passage, not just inward, but through to another region of space-time. A wormhole, a bridge. These solutions are mathematical, not physical. They show what's possible within the equations, but that doesn't mean they occur in nature. Most physicists believe these structures, if they ever existed, would be unstable. Any small disturbance, a particle of dust, a photon of light, would cause the structure to collapse or close. So the idea of a black hole leading to another universe or another part of our own is still speculative. Even so, the singularity remains central to the question. It represents a kind of ultimate destination. Not a bottom you can land on, but a state you can't pass through. It's the endpoint of the trajectory that starts when you fall past the event horizon. But not everyone agrees that the singularity is real. It may simply be a placeholder, a sign that our understanding is incomplete. a warning that general relativity, powerful as it is, isn't the full story. When densities get that high, when scales get that small, quantum mechanics has to come into play, and we don't yet have a theory that fully combines gravity with quantum physics. That's where research into quantum gravity begins. The hope is that at very small scales, the laws of the universe prevent true singularities from forming, that instead of a point of infinite density, matter is compressed into an incredibly small, but still finite region. Maybe there's a minimum size, a smallest possible volume, where pressure, energy, and the fabric of space itself push back. If that's the case, then black holes don't end in mathematical failure. They end in something new, something we haven't discovered yet. Some models propose that the core of a black hole becomes a kind of remnant, a stable structure where matter exists in a new state, not ordinary atoms, not neutron matter, but something more exotic. Others suggest that the information about what fell in is stored at the event horizon itself, encoded somehow in the surface area. These ideas try to preserve the principles of quantum mechanics, which don't allow for information to be destroyed. In all these cases, the singularity is replaced with something physical, not visible, not accessible, but finite. A bottom of sorts. One that exists not as a point, but as a region where the rules change. It's also possible that the interior of a black hole doesn't contain a static endpoint at all. That instead of a single place where all paths lead, the interior is dynamic, constantly changing, influenced by what falls in, shaped by time and matter and gravity in ways we can't predict from the outside. But no matter which model you choose, they all agree on one thing. Once you cross the event horizon, your future ends at the centre. Whether that centre is a singularity, a quantum remnant, or something else, you're headed there. You can't pause, you can't orbit, you can't avoid it. It's not because of pressure or force, it's because of geometry. The way space-time is curved inside the horizon removes every other path. To an outside observer, that journey is never seen. The signals stop, the image fades, the timeline breaks. But from the inside, from the frame of the falling object, the path continues. It's not immediate, but it's inevitable. There is a place you're going, a point you will reach, and once you do, the idea of time, of space, of motion, all of it becomes meaningless. So is there a bottom? Maybe. Not in the usual sense. Not in a way that allows us to visit, to send probes, to record what happens and send the data home. But something exists at the end of the fall. Some structure, some process, some limit. We don't know what it is. Our equations collapse before they tell us. But the signs suggest it's there. Waiting. Quiet. Hidden. And that raises another question. If we can't reach the bottom, if the interior is cut off from observation, then what does the black hole give back? If anything falls in and never returns, is that truly the end of the story? Or is there a way, even a slow, subtle one, for something to come out? Black holes grow when they take in matter. Gas, dust, stars, even light. Anything that crosses the event horizon adds to the total mass. There's no limit written into the structure of a black hole that says, this is enough. They don't cap out. They don't reject more mass. If something falls in, the black hole becomes more massive. Its gravity strengthens. Its event horizon expands. But in practice, growth depends on opportunity. A black hole in deep intergalactic space, far from stars or gas clouds, won't grow quickly. It might not grow at all. It just sits, heavy, invisible, and still. It takes something close, something nearby and falling inward, to start the process again. So the real question isn't whether black holes can grow without limit. It's whether the universe gives them the conditions to do so. The largest black holes we've observed, in the centres of the biggest galaxies, have masses in the tens of billions of solar masses. These giants didn't form in one step. They built up over time. They absorbed material during galaxy mergers. They pulled in gas from chaotic early environments, and they may have merged with other black holes along the way. Theoretically, there's no hard upper limit to how massive a black hole can become. It depends entirely on how much matter falls in and how fast. But growth isn't always smooth. There's a rate limit, not from the black hole itself, but from the physics of the material around it. When gas falls toward a black hole, it doesn't fall straight in. It forms an accretion disk. That disk heats up as material spirals closer. It glows, it emits radiation, and that radiation pushes back. If the gas is falling in quickly, the radiation pressure can become strong enough to resist further infall. This creates something called the Eddington limit, a balance point where the outward force of radiation equals the inward pull of gravity. If a black hole is accreting at the Eddington limit, it's growing as fast as it can without blowing away the surrounding material. Go above that, and the system becomes unstable. The gas is pushed away faster than it can fall in. Go below it, and the black hole grows more slowly. Some black holes accrete at the Eddington limit for long periods. Others fluctuate depending on the environment. In active galaxies, especially in the early universe, black holes may have grown faster than expected, either because the gas was dense enough to ignore radiation pressure, or because the infall happened in bursts. Super-Eddington accretion, brief periods of growth above the usual rate, might help explain how some black holes became so massive so quickly. Still, these growth phases don't last forever. As the material gets consumed, the inflow slows, the disk fades, the black hole enters a quiet phase, and unless something new falls in, it remains that way. Even the most massive black holes probably haven't reached the theoretical maximum. There may be black holes out there, unseen, undetected, with even greater mass, especially in regions where large galaxies have merged repeatedly over cosmic time. Some estimates suggest that a black hole could, in principle, grow to hundreds of billions of solar masses, or more. But eventually the environment changes, galaxies run out of nearby gas, stars stabilize in long orbits, the black hole's feeding becomes occasional instead of constant, and the growth slows, not because the black hole resists it, but because the universe becomes less generous. And there's another effect. As black holes grow more massive, their ability to pull in matter doesn't scale equally. The event horizon increases, yes, the gravity deepens, but the material around them also thins out. There's less nearby to draw in. Even in dense galactic centres, there's a balance between the black hole's influence and the structure of the galaxy itself. Stars don't collapse inward, they orbit, and unless something disturbs them, they stay far from the danger zone. This means most of the time, even supermassive black holes are not feeding actively. They wait, and sometimes they wait for millions of years. In that time, they don't decay, they don't shrink, they just persist, massive, quiet, unchanged. Some scientists have asked whether black holes could grow so large that they start to influence the expansion of the universe itself, not individually, but as a population. There are billions of galaxies, and many have black holes at their centres. Could their combined gravity pull against cosmic expansion? The answer appears to be no. The universe is expanding at a rate that far outpaces the gravitational influence of black holes, even when added together. The energy driving that expansion, called dark energy, doesn't get diluted by mass in the same way. So while black holes are massive, and their effects are strong locally, they don't seem to have the ability to reverse the overall trend. There's also the idea that black holes might stop growing not because of what's around them, but because of what they become. Some theories suggest that black holes formed in the early universe could grow into new kinds of structures. Not traditional black holes, but something stranger, something governed by quantum rules. These ideas are speculative, but they remind us that growth might mean more than just size. It might mean transformation. But from everything we've observed so far, growth is gradual. It depends on supply, it depends on time, and it depends on what the universe provides. There's no upper limit written into the laws of physics. There's only the practical question. Is there enough material left? Enough matter? Enough collisions? Enough density to feed a black hole for long enough that it becomes something larger than anything we've seen? We don't know, but we might find out, because some black holes are still growing, quietly, steadily, in the centres of galaxies we haven't studied yet. We're used to thinking about limits in physical terms. You fill a glass, it overflows, you eat a meal, you get full. But a black hole isn't a container. It doesn't store material in a space that can be filled up. It doesn't reach a point where it's too full to take in more. If something crosses the event horizon, it becomes part of the black hole. There's no barrier where material piles up or gets rejected. So, in the simple sense, no, black holes don't get full, not the way objects do. But that doesn't mean they grow without resistance. When a black hole is surrounded by matter, a disk of gas, dust or debris, that material has to lose energy before it can fall in. It spirals slowly, getting hotter and thinner, shedding momentum as it draws closer. That's a process that takes time, and it's not always efficient. In some systems, the gas heats up so much that the resulting radiation pushes against the incoming flow. The pressure slows the infall. In extreme cases, it can even stop it temporarily. This is the same principle that sets the Eddington limit. It's not a hard limit in the structure of the black hole. It's a balance in the environment around it. The more material falls in, the more energy is released, and that energy pushes outward. If the inflow is too fast, the system stabilizes by pushing some material away. But the black hole itself never refuses mass. It doesn't resist being added to. It just accepts what gets close enough to pass the horizon. Whether that happens slowly or quickly depends entirely on what's happening outside the black hole, not inside it. And sometimes, the outside simply runs out. In many galaxies, especially older ones, the central black holes have already consumed most of the nearby material. The remaining stars keep their distance. The gas has either fallen in or been pushed away by radiation and jets during earlier, more active phases. There's nothing left to accrete. In these cases, the black hole isn't full, it's just not being fed. We see this in galaxies with quiet cores. No X-ray glow, no jet, no sign of current accretion. The black hole is still there, still massive, still pulling inward. But with no fuel, there's no activity. It's not sleeping. It's just waiting. If more material arrives, maybe from a passing gas cloud or a galaxy merger, the process starts again. The black hole doesn't have to prepare. It doesn't change state. It simply resumes accretion. The disk forms, the light returns, and the black hole grows. Even when a black hole is accreting near its maximum rate, the structure doesn't change to resist that. There's no pressure build-up, no stretching or expansion that causes it to burst or reject material. Its growth is quiet and one-directional. Mass goes in, and the event horizon grows slightly larger. There's a related question that sometimes comes up. If black holes can grow forever, could they eventually consume everything? The answer is no, and it has nothing to do with being full. It has to do with distance, motion, and time. Most of the matter in the universe is too far away, too stable, or moving in orbits that keep it safely outside the reach of any black hole. Even in dense regions, most stars and systems follow paths that don't bring them near the centre. Gravity is strong, but it falls off with distance. Unless something actively brings an object closer, a disturbance, a collision, a change in trajectory, it won't fall in. So even as a black hole grows, it's not pulling everything toward it. Its sphere of influence remains limited. The region where it can dominate motion, called the gravitational radius of influence, depends on its mass and the environment. But even for the largest black holes, that radius is a small fraction of the galaxy. This is why we don't need to imagine black holes getting full. Their limits are set by the universe around them, not by anything internal. They don't stop growing because they reach a cap. They stop because the conditions for growth fade. Sometimes that's temporary. In the early universe, black holes had more fuel. Galaxies were smaller, more chaotic, and full of loose gas. Feeding was easy, accretion was fast, but over time that changed. Gas was consumed, systems stabilized. the violent early phase passed, and black holes entered long periods of quiet. And yet they're still there, silent, steady, waiting. If something new comes along, they'll grow again. Not because they're hungry, not because they're empty, but because they're always open. There are rare moments when black holes seem to reject something, not permanently, but temporarily. A star gets close, it begins to fall in. Radiation builds up, some of the material is pushed away, only a fraction makes it across the horizon. But that's not the black hole being full, it's the environment pushing back. The balance between inward and outward force shifts constantly. Sometimes material falls in slowly, sometimes it piles up outside, forming a thick disk. Sometimes it disperses entirely. But none of this is because the black hole has a limit inside it. There's no chamber that fills, no threshold that triggers a response. From the outside, a black hole looks like a simple thing. Mass, spin, charge. No internal structure, no visible surface, no place for overflow. So instead of asking whether they ever get full, it's more accurate to ask how long they go between meals, because a black hole will take in what's given to it, for as long as the universe allows. The end isn't determined by appetite, it's set by opportunity. And when that opportunity comes from another black hole, something even more interesting happens. When two black holes merge, it's not like two solid objects colliding. There's no crash in the way we might imagine it, no explosion of matter, no scattering of debris. Both black holes are already made of curved space-time, and when they come close enough, the curves combine. What actually happens is a slow, spiralling dance. The two black holes orbit each other, gradually losing energy. That energy doesn't disappear. It's carried away by gravitational waves. These waves stretch and squeeze the fabric of space-time as they move outward. They're weak by the time they reach us, but they're real. We've measured them. The closer the black holes get, the faster they orbit. The frequency of the gravitational waves increases, the amplitude rises, and then, in the final moments, they merge. The event horizons touch. The space between them vanishes. What's left is a single black hole, slightly smaller than the sum of its parts, because a fraction of the mass was carried away as energy. The merger itself takes only a few milliseconds. From the outside, it looks like a final sharp burst of gravitational waves, followed by quiet. There's no visible light unless there's gas nearby being disturbed. In pure vacuum, it's all gravity. And then, just like that, there's one black hole where there used to be two. The new black hole doesn't wobble for long. It settles into a stable shape quickly. The event horizon becomes smooth. The spin adjusts. And from that point forward, it behaves like any other. Massive, silent, and undetectable, except through its effect on the space around it. So what's different after a merger? The most obvious change is mass. The new black hole is more massive than either of the originals, though slightly less than their total combined mass. That difference, usually a few percent, was radiated away as gravitational energy during the merger. Depending on the size of the black holes involved, that energy release can be enormous. In some events we've detected, the amount of energy emitted in gravitational waves is greater than the output of all the stars in the universe, for a brief moment. The next change is spin. The final black hole often spins faster than either original. The direction and speed of that spin depend on the orientation of the original pair. If both black holes were spinning in the same direction as their orbit, the result can be a high spin remnant. If they were misaligned, the final spin might be less extreme, but either way, the merger shapes the internal properties of the new black hole in measurable ways. These properties, mass and spin, are all we can observe. After the merger, the history disappears. There's no way to tell what the original black holes looked like, how long they orbited, or what paths they took to get there. Everything gets absorbed into the final mass and motion. No trace remains of the individual identities. This loss of information raises deeper questions, ones physicists are still trying to answer. If information is preserved in the universe, then how is it stored when two black holes become one? Does it survive in some encoded form on the event horizon? Is it lost completely? Or does the black hole somehow keep track in a way we haven't yet understood? The information paradox, the idea that something is lost during black hole interactions, becomes even more complicated after mergers. It's not just about one black hole swallowing matter. It's about entire systems combining and emerging as something new, with none of the old structure left behind. But setting those theoretical questions aside, what we can say is this. After a merger, the universe is changed. A heavier black hole now exists. Space-time in the surrounding region has settled into a new shape. And somewhere far away, a gravitational wave has passed through, stretching distances briefly before fading forever. Sometimes the newly merged black hole stays where it is, especially if the merger happened at the centre of a galaxy. But in other cases, the merger imparts a kick, an actual motion. The final black hole may be pushed in one direction due to the asymmetric release of energy. These kick velocities are usually small, but in some scenarios they can be large enough to move the black hole out of the centre of its galaxy. In extreme cases, it could even be ejected into intergalactic space. We've looked for signs of these recoiling black holes, objects moving alone, outside the usual centres. Some candidates have been found, but they're rare. Most merged black holes remain where the conditions were right to form them in the first place. And while we've observed many individual merger events through gravitational wave detectors, the long-term fate of these post-merger black holes remains quiet. They continue on. They wait for new material, they orbit silently in space, and in time they may merge again, with another black hole, if conditions allow. There's no mechanism that says this is the final one. A black hole that forms from a merger can go on to merge again. There's no decay, no memory loss, just new properties and a continued ability to grow. So what happens after they merge? They stabilise, they persist, and they continue to curve space around them. The image of a black hole swallowing everything, stars, galaxies, eventually the entire universe, feels dramatic, maybe even a little terrifying. It taps into something instinctive, the fear of being pulled in, of being erased. But when we ask whether a black hole could actually consume the universe, we're not talking about emotion or metaphor. We're asking something specific about the structure of space, the rules of gravity, and the scale of the cosmos. And the answer, as far as we know, is no. A black hole, no matter how massive, can't swallow the universe. Not because it wouldn't try, but because the universe is expanding, and that changes everything. Black holes grow by accreting mass. That mass has to be nearby, or at least close enough that the black hole's gravity can overcome any outward motion. In the early universe, this was easier. Matter was closer together. Gas clouds were denser. Galaxies were younger and smaller, and black holes had more material available. Growth was fast, but over time that changed. The universe expanded. Distances between objects increased, and at a certain point, the rate of expansion became more than just noticeable. It became dominant. Today, the space between most galaxies is growing, not because galaxies are flying apart through space, but because space itself is stretching. That expansion isn't caused by black holes. It's driven by dark energy, a property of the vacuum that causes the large-scale structure of the universe to accelerate outward. This has important consequences for black holes. It means that no matter how massive a black hole becomes, there are regions of space moving away from it faster than light. Not in the local sense. Nothing breaks the speed of a light in its own frame, but in the sense that the space between them is expanding so fast that light, or gravity, or anything else can't cross the gap. That's the cosmic horizon. Beyond that point, objects are receding too quickly for any influence to reach them. They're permanently out of contact, so even if a black hole could, in principle, pull in everything it could reach, there's a hard limit. The expansion of space wins beyond a certain scale. It's not that the black hole becomes weaker. It's that the universe grows faster than gravity can keep up with. That's why we say a black hole can't swallow the universe, not because the black hole lacks strength, but because the universe isn't standing still. The game board is moving, and even within galaxies there are boundaries. A supermassive black hole at the centre of a galaxy can influence stars for tens of light years. It can affect the orbits, pull in gas, and occasionally consume something large. But most of the stars in the galaxy are too far away. They orbit slowly, safely. They're gravitationally bound to the galaxy, not to the black hole itself. And unless something disturbs their path, a collision, a slingshot interaction, a tidal shift, they won't fall in. Multiply that by billions of galaxies, each with their own black holes, and the picture becomes clear. Yes, black holes can grow, but no, they're not vacuuming up the universe. Their reach is limited, their influence is local. There's also the issue of time. Even if a black hole had infinite time to grow, the expansion of the universe would keep placing more of the cosmos out of reach. The gap between objects isn't closing, it's widening, and the rate of that widening is accelerating. Eventually, in the far future, every galaxy beyond our local group will recede past the cosmic horizon. We won't be able to see them anymore. No telescope, no signal, no particle from those regions will ever reach us again. The black holes in those galaxies will be isolated, not because they've swallowed everything, but because the universe has pulled everything else away. Even within the local group, black holes will eventually run out of fuel. Stars will burn out, gas will disperse, mergers will become rare, and black holes will stop growing, not because they're full, but because they're alone. The future is cold and long. Black holes, over trillions of years, will remain as some of the last structures still intact. But they'll be quiet. No feeding, no merging, just slow evaporation through a process called Hawking radiation, a tiny release of energy at the edge of the event horizon. Too small to detect now, but over unimaginable timescales, it's enough to make even black holes disappear. So when we ask whether a black hole could swallow the universe, we're really asking about scale, and about motion, and about how the structure of space prevents any one thing from dominating everything else. Black holes are powerful, but they're part of the universe. They don't escape its rules. They follow the same expansion. They obey the same limits. And in the end, they exist within a system that is bigger, faster, and more complex than gravity alone. Black holes are often described as destroyers, places where things go and never return, where structure, information, and even light disappear. But if they only erased, they wouldn't tell us much. And yet they do. Over and over again we see signs, evidence left behind not by what went in, but by the effect of its going. The most obvious legacy of a black hole is gravitational. Mass doesn't vanish, it changes form. And when something becomes part of a black hole, that mass still curves the space around it. The black hole keeps growing, and that growth affects its surroundings. Stars orbit differently. Gas settles in new patterns. The galaxy feels the change. We can detect this. We can measure the motion of stars near the centre of galaxies and infer the mass they're orbiting. In the Milky Way, for example, a group of stars near the centre follow tight, fast paths. They curve sharply around an invisible point. We've mapped these paths for decades, and they leave no doubt. Something massive, something compact, is there. We call it Sagittarius A. We can't see it, but its influence is obvious. That influence is one kind of trace, a record of what the black hole contains, not directly but gravitationally. And gravity doesn't fade quickly. It shapes the galaxy long after the black hole has stopped growing. Another legacy is light, or more precisely the absence of it. Black holes don't emit light, but the things falling into them often do, before they cross the horizon. Accretion disks can glow with X-rays and other high-energy radiation. Jets can fire particles across vast distances. When these signals stop, or when they change suddenly, they leave behind a kind of silence, a gap. And in that gap we find the edge of something invisible. We also see echoes, Not sound, but reprocessed light. A star gets disrupted, a flare appears, that light bounces off nearby gas or dust. It travels at different angles and times. We detect those echoes years later, like ripples in a pond after the stone has sunk. They don't tell us what the black hole is now, they tell us what happened before, and from those traces we build a timeline. But the legacies aren't just distant or faint. Some are structural. Galaxy cores can be reshaped by black hole activity. Whole clusters of stars might be missing from the central region, a sign that black holes have merged, interacted, and flung material outward. These effects persist for millions of years. They change the structure of galaxies. They sculpt emptiness. In other cases, black holes leave behind movement, recoil. When two black holes merge, the resulting object can receive a kick, a push from the asymmetry of gravitational wave emission. That motion continues. It doesn't stop. The black hole carries its history with it in velocity. If it's fast enough, it might move away from the centre. If it's extreme, it might leave the galaxy altogether. There are even cases where black holes leave behind light indirectly, through their influence on nearby systems. A passing black hole might disturb a star system, sending one star inward and the other outward at extreme speed. We've detected stars moving faster than anything else in the galaxy, so-called hypervelocity stars. Their trajectories suggest an interaction with something massive, dark and compact, something like a black hole. And then there's the deepest kind of legacy, the question of information. When a black hole forms, it inherits the mass, spin and charge of everything that fell in. But it doesn't preserve the details, at least not in any way we can detect. If a black hole swallows a star, the structure of that star is gone. Its layers, its fusion state, its history. None of that leaves a mark. Only the final totals, the summed values. This is the foundation of the black hole information paradox. If the universe is truly governed by reversible laws, where information is never destroyed, only transformed, then black holes seem to violate that. They erase the differences between things, and if they eventually evaporate, as Hawking radiation predicts, what's left? The radiation carries away energy, yes. But does it carry away information? Or is it random? Do the quantum fluctuations at the event horizon somehow encode the history of everything that's fallen in? Or is the information truly lost? No one knows yet. The best minds in physics are still debating it. And until we have a working theory of quantum gravity, one that combines general relativity and quantum mechanics, we probably won't know for sure. But in the meantime, black holes leave behind other kinds of evidence. Movements, emissions, shadows, silence. Each one is a record of what happened. Not a full account, but enough to trace the shape of events. They don't leave behind ruins. There are no remnants, no debris, no burned out cores. Just curves in space, twists in motion, patterns in radiation, all of them signs of something dense, something invisible, something permanent. And perhaps the most lasting thing they leave behind is the question itself, a constant challenge to our understanding, a reminder that even in a universe ruled by consistent laws, there are still places we can't see into, still processes we can't fully trace, still consequences we haven't fully mapped. In that way, black holes leave behind more than absence. They leave a frontier, and the farther we look, the more of them we find. If black holes grow by swallowing matter, and if they don't get full in the traditional sense, then is there anything, anywhere, that actually puts a stop to them? Some hard boundary, not based on distance or supply, but written into the rules themselves. A true physical limit. It's a reasonable question. Everything else in the universe seems to have thresholds. Stars collapse when they get too heavy. Atoms break apart above certain energies. Even light is subject to maximum speeds and behaviour changes at small scales. So where's the line for black holes? One possible answer is there isn't one, not a strict universal ceiling. General relativity, the theory that describes how black holes form and behave, places no upper bound on how massive a black hole can become. The more mass it contains, the larger the event horizon, the stronger the gravity, the deeper the well, and the rules hold, even at extreme scales. But there's a difference between what's mathematically allowed and what the universe actually does. Just because no rule says stop here doesn't mean it happens freely in practice. We've observed black holes in many mass ranges. Stellar mass black holes formed by collapsing stars typically fall between about 3 and 50 times the mass of the Sun. Supermassive black holes found at the centres of galaxies can reach millions or billions of solar masses, and in between we've begun to find evidence of intermediate mass black holes. The missing link. Still rare, still under study. But even the biggest black holes we've seen, so far topping out around 60 billion solar masses, don't represent a fundamental boundary. They're just the largest ones nature has had time and material to build. Could larger ones exist? The math says yes, but the conditions needed to form them might be rare, or might not occur at all. There are a few ideas about how physics might eventually step in. One is based on accretion. As a black hole grows, its feeding becomes more disruptive. Radiation from infalling material pushes away gas. Jets can eject matter across galaxies. At a certain point, this feedback might self-regulate the process. The black hole gets big enough to limit its own fuel supply, simply by how violently it reshapes its environment. That's not a hard cap, it's a practical one. The physics still allows more growth, but the system becomes less efficient. Galaxies stabilize, material gets pushed too far away to fall in, and so the black hole grows more slowly, or stops entirely. Another possibility comes from the structure of galaxies themselves. Observations suggest a rough relationship between the mass of a central black hole and the mass of the galaxy around it, specifically the bulge of stars at the centre. It's not a perfect rule, but the correlation holds across many systems. That may point to a co-evolution process. Black holes and galaxies grow together, and one limits the other. If so, then there's an indirect limit, not because of what black holes are, but because of what galaxies become. And then there are more speculative ideas, rooted in physics we don't fully understand. Some theories suggest that black holes aren't entirely classical, that deep inside, near the singularity, quantum effects become important. If so, then extremely massive black holes might undergo internal changes, shifts in structure, states we don't yet have the math to describe. In that view, the limit wouldn't come from space getting too curved, but from the breakdown of the assumptions we've used to describe it. Still others look at entropy. Black holes have entropy, a measure of disorder, or the number of possible internal states. The more massive the black hole, the more entropy it contains. This is tied to the area of the event horizon. As mass increases, the surface area grows, and so does the entropy. There's no known ceiling for that, but at extreme scales, it might tell us something about information storage, or the total capacity for encoding the past. But even these considerations don't set a firm, observable limit. They don't say, beyond this, black holes can't exist. They only suggest that something unusual might happen if one were to grow large enough. And yet, nothing we know stops them in principle. There's no physical law that blocks a black hole from being 100 billion solar masses, or more. The only constraints come from the environment, the material available, the time it takes, the expansion of the universe. Eventually, over cosmic time, even the largest black holes will stop growing. Not because of a physics barrier, but because the universe changes. Galaxies separate. Fuel runs out. The conditions that allowed black holes to grow no longer exist. And much further out, far beyond any practical scale, Hawking radiation becomes important. This is a quantum process, slow beyond comprehension, in which black holes emit tiny amounts of radiation and gradually lose mass. For small black holes it's negligible. For large ones, it's even slower. A black hole with the mass of our Sun would take something like 1067 years to evaporate. A supermassive black hole? Multiply that again and again. But eventually even these would fade. So maybe that's the true limit. Not mass, not size, but time. Black holes aren't infinite, they're just long-lasting. Long enough to feel eternal. But they still exist within a universe that changes. And whatever they become in the distant future, whether they fade slowly, shift into new states, or reveal physics we haven't yet written down, their behaviour now suggests that if there is a limit, we haven't found it. Not yet. Nothing we've observed suggests that black holes vanish suddenly. They don't flicker out like failed stars. They don't collapse into something smaller. In every case we've studied, black holes are persistent, stable, long-lived, and remarkably quiet once their growth slows. But the question remains, do they disappear? Do they ever stop being black holes? The answer is yes, at least in theory, but not in any way that happens quickly. In the 1970s, Stephen Hawking proposed that black holes aren't perfectly black, that they radiate just a little because of quantum effects near the event horizon. This idea, now called Hawking radiation, suggests that black holes slowly lose mass over time. Not through accretion, not from anything falling in, but from energy leaking out. It's a strange idea, and not an intuitive one. It doesn't come from gravity or heat or pressure. It comes from the way empty space behaves near intense gravitational fields. In quantum theory, space isn't empty. It's full of fluctuations. Particle-antiparticle pairs appear and disappear constantly, normally cancelling each other out. But near a black hole's event horizon, these pairs can become separated. One falls in and the other escapes. From the outside, it looks like the black hole has emitted a particle. It has lost a little energy, a little mass. This loss is incredibly slow. For a black hole with the mass of a star, the radiation is so faint that it's practically zero on any observable timescale. The cosmic microwave background, the leftover glow of the Big Bang, is still warmer than the Hawking radiation such a black hole would produce. So instead of radiating away, the black hole absorbs more heat than it emits. But as the universe cools and as time stretches forward far beyond stars and galaxies, that balance shifts. Eventually the background radiation drops below the temperature of the black hole, and from that moment on, the black hole begins to lose mass faster than it gains it. Still, this isn't fast. A stellar mass black hole might take 1067 years to evaporate. That's a 1 with 67 zeros. A supermassive black hole, millions or billions of times heavier, would take vastly longer. Trillions of trillions of trillions of years. We're talking about timescales that stretch far beyond the current age of the universe, which is just 13.8 billion years by comparison. During this evaporation, the black hole doesn't shrink like a balloon. It remains gravitationally intense, even as its mass slowly decreases. The process accelerates near the end. As the mass drops, the temperature rises. The radiation becomes more energetic. In the final moments, if the theory holds, the black hole disappears in a brief flash, a final release of energy. We've never observed this. It's far too slow, far too faint, and far too distant in the future, but the math supports it. If quantum mechanics and general relativity both apply, then black holes don't last forever. They age, they radiate, and they go. Some physicists have questioned this picture. They've asked whether black holes really disappear entirely, or whether something remains, a core, a remnant, a new kind of particle or structure too small to detect. We don't know. There's no experiment we can run yet that reaches far enough, waits long enough, or sees clearly enough to find out. Other theories suggest that the radiation itself contains information, that nothing is truly lost. But if that's true, it would mean the process of disappearance isn't as simple as mass turning into heat. It would mean the black hole slowly, subtly, encodes everything it swallowed into the radiation it emits. Not in a way we can easily read. but in a way that preserves the rules of physics? That's still an open question. For now, the best we can say is this. Black holes do seem to disappear, eventually. Not by collapsing or being destroyed, but by releasing their energy bit by bit until nothing is left. And even that nothing might be more complicated than we think. But that evaporation doesn't affect the universe around them in any meaningful way. It's too slow, too subtle. It doesn't blow things apart, it doesn't reshape galaxies. It just marks the quiet, final phase of something that once was the densest object in space. Until that happens, though, they remain. Dark, heavy, silent. And if you were to look at one today or 1 billion years from now, it would seem unchanged. The event horizon of a black hole isn't a wall. There's no visible boundary, no signpost or transition. If you were falling in, you wouldn't feel it. You'd pass the horizon just like any other point in space, silently, without friction, without any signal that something irreversible had just happened. But from that moment on, your trajectory would be fixed. There'd be no way back. That's what makes black holes different from anything else in the universe. The event horizon isn't just a region of strong gravity, it's a boundary in space-time where the direction of travel changes. Inside the horizon, all possible paths lead inward. No force, no signal, no action can send anything back out. Even light, which normally outruns everything, can't escape. So once you cross that line, you're committed. But committed to what exactly? It depends on the size of the black hole. In a stellar mass black hole, the kind formed from the collapse of a star, tidal forces increase sharply near the horizon. Gravity at your feet would be significantly stronger than gravity at your head. You'd be stretched, pulled lengthwise, compressed from the sides. This process has a technical name, but it's often called spaghettification, and it happens fast. Long before you reach the singularity at the centre, you'd be torn apart. But in a supermassive black hole, like the ones at the centres of galaxies, the gradient in gravity near the horizon is gentler. The event horizon is much farther from the singularity, and tidal forces are weaker at that distance. You could cross the horizon without being destroyed right away. In fact, you might not feel anything unusual at all. For a brief moment, maybe even minutes, it would feel like ordinary space. But everything around you would change. You'd stop receiving signals from the outside. Light from the universe beyond the horizon would be redshifted, stretched into longer wavelengths, until it faded entirely. Space itself would feel distorted, not visually but structurally. Directions that once led outward would now curve inward. Your motion, your momentum, would guide you toward the centre, and you wouldn't be able to change that. From your point of view, time would move normally. Your thoughts, your heartbeat, your sense of motion, all of it would feel continuous. But from the outside, something very different would be seen. To an external observer, your fall would appear to slow down, you'd dim, stretch, fade. Your final signals would take longer and longer to arrive, until eventually none of them would. Not because they stopped, but because they couldn't escape. Inside the black hole, space and time trade roles in a way. The inward direction becomes a kind of forward in time, not metaphorically but mathematically. The singularity isn't just a point in space, it's a moment in your future, and like all future moments, you can't avoid reaching it. But what you'd experience near that singularity is still unknown. Our equations break there. The curvature of space-time becomes infinite. Distances shrink to zero. Quantum effects take over, but we don't yet have a complete theory that combines them with gravity. Some models suggest that matter is crushed into an infinitely dense point. Others propose a quantum foam, or a remnant, or a bridge to something else. But there's no data, no observation, only theories. If you were conscious, falling in, you might never reach that moment in any meaningful sense. The journey ends before it can be processed. For small black holes, the end comes quickly, violently. For large ones, it might be slower, but no less final. You wouldn't fall through a tunnel, You wouldn't emerge somewhere else. Wormholes, white holes. Those are mathematical ideas, not observed realities. And nothing in our current understanding suggests that falling into a black hole leads to travel through space. It leads to the centre, to the end of space-time. But even in that finality, something remains. Your mass becomes part of the black hole's mass. Your motion, your momentum, your energy, all absorbed. From the outside, none of the details can be recovered. But the influence continues. The black hole grows. Its event horizon expands. The curvature around it deepens slightly, and your presence, though undetectable, changes the shape of space. And perhaps that's the most remarkable part, that even something as destructive as a black hole still obeys the rules. It doesn't erase you arbitrarily. It absorbs you according to laws we can trace. It becomes a new thing, slightly different, slightly larger, and then it continues. From the outside, nothing looks different. The surface is still smooth, no markings, no indication of what went in, but the change is real. It's permanent, and it's measurable, even if only indirectly. So what would it feel like to fall in? It would feel like falling through silence, through distance, through space that no longer includes an exit. And yet, it's still part of the universe, even in its isolation, even in its finality. If black holes are the strongest gravitational objects in the universe, why don't they dominate it completely? Why isn't everything drawn toward them? Why doesn't every galaxy collapse inward, every star pulled off its path, every orbit lost to that dark centre? The answer starts with distance. Gravity weakens with separation. It's still infinite in reach. It never drops to zero, but it fades quickly. Double the distance, and the pull drops by a factor of 4. Triple it, and it drops by 9. That decay matters, because while black holes are massive, most of the universe is far away from them, and at a distance, even a supermassive black hole starts to look like just another object with mass. Inside galaxies, stars orbit the centre, but they're not falling in. Their motion balances gravity. The same way the Earth doesn't fall into the Sun, it's moving sideways fast enough that it stays in orbit. That same principle applies on much larger scales. Stars orbit the galactic centre, including the black hole, but they're not spiralling inward unless something disturbs them. Most of the time, nothing does. Black holes don't pull any harder than their mass allows. They don't have magical suction. A black hole with the mass of the Sun pulls just as strongly from a distance as the Sun itself did. The difference shows up close in when you get near the event horizon. That's where things change. That's where escape becomes impossible. But at ordinary distances, there's no special pull. Just gravity, following the same rules as always. That's why black holes don't consume everything around them. They don't have the reach. They can't override the structure of orbits, the stability of systems, or the scale of the universe. Galaxies are held together by more than their central black holes. Most of the mass is elsewhere, in stars, in gas, in something we call dark matter. That mass creates its own gravitational field. It shapes rotation curves and structure. The black hole at the centre contributes, but it doesn't rule. It's a part of the system, not its master. Even in galaxy clusters where thousands of galaxies interact, the dominant forces aren't black holes. They're the mutual pull of all the mass, visible and invisible, plus the motion of galaxies themselves. Black holes influence their local environments, yes, but those environments are small compared to the scale of the cluster, or the universe. And there's another factor, cosmic expansion. On the larger scales, gravity isn't the only force shaping motion. The universe is expanding. That expansion stretches space itself. It increases the distance between galaxies, not by pushing them through space, but by changing the fabric of space between them. And that change is accelerating. Black holes can't stop it. They're gravitationally bound to their local structures, but they don't push back against the universe's expansion. Once a region of space moves beyond their reach, that's it. There's no pull strong enough to reclaim it, so they don't take over, not because they're weak, but because the universe is large, active, and in motion. Everything has inertia, everything has momentum, and black holes, for all their strength, obey the same rules. Even within their own galaxies, most black holes spend the majority of their time inactive, not because they're out of power, but because they're out of fuel. There's no endless stream of matter falling in. There are quiet periods, sometimes millions of years long, where nothing approaches the horizon. The black hole waits. Massive, yes, but passive. Occasionally a star drifts close. A gas cloud collapses. A merger brings in new material. The black hole flares, feeds, grows, then it goes quiet again. So when we ask why they don't rule everything, we're really asking why the universe isn't dominated by collapse, why it hasn't all fallen inward. And the answer is, because the universe is balanced. Not perfectly, not forever, but enough. Gravity pulls, but motion resists. Collapse threatens, but orbits persist. Black holes form, grow, merge, but always within a larger context that contains them. They don't expand on their own. They don't spread. They grow when fed, and they rest when not. That's not a flaw. It's what keeps the universe open. So yes, they're powerful. But they're not kings. They're not engines of destruction sweeping the cosmos clean. They're parts of systems, products of collapse, bound by the same physics that made them. There's a question that comes up in the background of all this. A quiet one. Not about what black holes do, but what they mean. Not just how they behave, but whether they tell us something about the shape of the universe itself. Because when you look at what defines a black hole, a boundary beyond which nothing returns, a space where time bends inward, a region where the horizon marks the edge of observation, some of those same ideas seem to echo at the scale of the cosmos. The observable universe has a horizon, a limit to what we can see, not because there's a wall, but because light takes time to travel, and the universe has only been around for a finite amount of time. Beyond a certain distance, there simply hasn't been enough time for light to reach us. That horizon expands as time goes on, but it's always there. A curved boundary set not by gravity, but by history. And the universe, as far as we can tell, is expanding. Not just the contents within it, but space itself. Galaxies are moving apart, not through space, but with space. The farther away something is, the faster it recedes. At some point, far enough out, that recession speed exceeds what light can bridge. Beyond that point, we can't interact. We can't even observe. Not because we lack instruments, but because causality itself has been cut off. This starts to sound familiar. A boundary. A region of no return. A place defined not by contents, but by limits on communication. Of course, the physics is different. The event horizon of a black hole marks a region where gravity has overpowered escape. The cosmic horizon marks a region where expansion has outpaced connection. One curves inward, the other stretches outward, but both represent edges, not physical surfaces, but transitions in what can be known or affected or reached. Some theories have taken this similarity further. They ask whether the entire universe could be described using the same mathematics that describes a black hole. Not in a literal way, not that we're inside one, but that the structure, the energy, the entropy, and even the information content of the universe might follow the same constraints. This leads to concepts like the holographic principle, the idea that the information inside a region of space might be encoded on its boundary. It sounds strange, but it's based on solid mathematical foundations. It suggests that the universe might, in some deep way, behave more like a surface than a volume. That what happens inside is a projection of the physics at the edge. And if that's true, then black holes aren't just oddities. They're clues. They're where these deep relationships between space, time, and information show themselves most clearly. Because when something crosses a black hole's horizon, we lose sight of the details. But the total effect, the mass, the spin, the charge, remains. The horizon keeps the tally. And that counting is what gives rise to some of the most powerful insights in modern physics. It suggests that horizons matter, that what we can't see still changes what is, that the limits of observation aren't just practical, they're fundamental. And in that sense, the universe itself may be more like a black hole than we thought. Not a trap, not an ending, but a region defined by relationships, between energy and curvature, between motion and limit, between past and possible. We don't know how far that idea goes. We don't know if the comparison holds at every level, but we do know that the quiet edge of a black hole, the event horizon, contains more than just a boundary. It contains information, history, entropy, geometry. And that might be true for the universe as a whole. In the end, the black hole is not just a curiosity, it's a kind of mirror. It shows us what space does under pressure, what time does under collapse, what matter does when it has no more room to fall. And it shows us that even in silence, even in darkness, there are rules, there is structure, there is something to learn. So wherever you are, drifting off, lying still, or just letting your mind wander, thank you for spending this time with Science for Sleep. There's always more to explore, more to ask, and plenty to leave unanswered, at least for now. Until next time, rest easy and sleep well.